In modern distributed architectures, achieving 100% functional test coverage is an illusion of safety against catastrophic production crashes. Functional testing only validates what a system does under normal conditions. It proves the code logic works. Non-functional testing validates how a system survives under the crushing pressure of scale, infrastructure failure, and targeted attacks. A minor logic error in a shopping cart can be patched with a quick hotfix, but non-functional flaws, like deep architectural bottlenecks, deadlocks, or memory leaks, are embedded in the system's foundation. Resolving them post-release requires complete system-wide rewrites, destroying business continuity and burning astronomical recovery costs. To categorize and defend against these infrastructure-level failures, engineers rely on the ISO IEC 2510 standard. It provides a definitive global framework for mapping out non-functional quality attributes. True survival requires abandoning subjective requirements like fast response times or secure data. Engineering teams must mathematically define strict service-level agreements before a single line of code is ever written. The sheer scope of non-functional quality is too broad for a single engineering discipline. It requires a strategic division of labor between the test analyst and the technical test analyst. This matrix outlines the ISO standard division. Test analysts handle user-facing metrics, measuring interaction capability, interface accessibility, and interoperability, ensuring flawless external API data exchange. The technical test analyst then takes over deep infrastructure mechanics, covering performance, reliability, security, and maintainability to analyze exact physical limits. The technical test analyst's objective is not to find everyday bugs. They construct a mathematical guarantee of system stability under extreme, unpredictable conditions. Performance efficiency testing evaluates three strict parameters: time responsiveness, resource utilization across CPU, memory, and disk I/O, and total system capacity measured in concurrent users. This scatterplot maps API response times, averages dangerously mask network jitter outliers. Analysts strip noise using trimmed means to isolate true tail latency. In microservices, a single delayed node bottlenecks the entire parent request, causing tail latency amplification. To accurately track SLA compliance, performance metrics cannot rely on typical response times. They must be strictly governed by tracking P90, P95, and P99 percentiles. Finding limits requires two distinct methods. Load testing applies expected peak traffic to identify standard bottlenecks. Stress testing pushes the system past its limits to find its breaking point, evaluating data integrity and graceful recovery when it inevitably crashes. Attempting to generate this immense load using GUI-level test scripts will fail. Heavy rendering exhausts the test generator's CPU and bandwidth long before the backend feels real pressure. True enterprise stress testing requires headless, protocol-level script injection. Communicating directly via gRPC bypasses client-side rendering entirely, mapping the true mathematical limits of the backend. Reliability is the statistical probability that a system will continuously operate without failure over a given amount of CPU execution time. The Jelinski-Moranda model mathematically predicts mean time between failures. The equation maps hazard rate, Z, using n, initial defects, and phi, the defect's failure contribution. The model graphs a perfectly stepped decline, theorizing the hazard rate drops sharply as bugs are removed. Availability calculations divide the mean time to failure by the sum of mean time to failure plus mean time to recovery. Achieving 4 nines of availability, 99.99% uptime, requires engineers to aggressively shrink the time it takes to recover from an outage. Mission-critical domains, like aerospace or core banking, enforce this recovery through N-version programming. Redundant, independently coded components run in parallel. A voter mechanism constantly compares their outputs, ensuring total fault tolerance if one component fails. Analysts validate resilience through intentional fault injection. They intentionally corrupt hardware pins, flip memory bits, and delay network packets to test safeguards. High reliability is achieved by assuming hardware and software will inevitably fail, and engineering the architecture to survive and automatically recover from those failures. Modern security testing defends 5 pillars: confidentiality, integrity, non-repudiation, accountability, and authenticity. This grid maps application security testing. Static analysis scans raw code early. Dynamic analysis attacks from the outside in, mimicking hackers. Interactive analysis combines both inside the application, lowering false positives. Finally, runtime application self-protection blocks zero-day attacks in real time. Effective security testing embeds a continuous series of overlapping diagnostic tools from the initial line of code to the live production environment. Executing these performance and security tests in a laboratory setting has a critical weakness. Applying massive but uniform synthetic load is useless if it does not match the actual statistical probability of real-world user behavior. To solve this, engineers implement software reliability pioneer John Musa's concept of the operational profile. This dashboard represents an operational profile. Analysts extract vast amounts of telemetry data from application performance monitoring tools to calculate the exact execution probability of every function in the system. Virtual users are assigned strict weights matching these probabilities. The test injects pseudo-random inputs to mimic reality, subjecting the database to heavily weighted, continuous read loads, contrasted against sparse, concurrent write loads. Enforcing an operational profile exposes the deep, chaotic concurrency race conditions and memory deadlocks that uniform testing misses. It bridges the gap between clean lab conditions and production reality. Discovering a fundamental architectural flaw, like a non-scalable database schema, during final system integration carries catastrophic financial and brand risk. This chart maps the Boehm-Basili cost of fix curve. It proves the exponential cost explosion of late-stage defect discovery. A structural flaw that costs pennies to fix during the design phase costs millions if found in production. The shift-left strategy neutralizes this curve by dragging technical reviews, security scans, and structural data flow analysis to the earliest planning and compilation phases. By neutralizing uninitialized variables and stripping unreachable code directly at the IDE level, engineers prevent cascading resource exhaustion long before the first load tests even begin. Moving technical validation to the earliest development phases builds architectural resilience into the code, preventing failures before they occur. By mathematically defining service-level agreements, modeling precise operational profiles, and continuously executing non-functional parameters from day one, engineering teams build the resilience required for systems to survive the volatility of production.